All right, so my presentation for today is going to be on fast RCNN. Okay, so I figured I'd kind of go into a little bit of an introduction because as I learned while I was kind of looking into all of this is that everything kind of builds on top of each other. So we start with what exactly is machine learning. So it is this evolving branch of computational algorithms that we use because they are designed to mimic human intelligence, which is kind of cool that it's able to do that. The algorithms within machine learning are trained by adapting their structure through repetition. So we have training data that we as humans make that we feed this algorithm, and it is the inputs with the desired outcomes. It's continuously and iteratively fed to the machine learning algorithm, and the algorithm is able to optimally configure itself to produce the desired outcomes with these training inputs, even to the point when it gets new input data that it doesn't already have like an associated output to, it's able to kind of work its way through to getting to a prediction. So machine learning is actually really cool because it comes from not just artificial intelligence, but all sorts of other fields like computer science, psychology, information theory, etc. Under this umbrella, we see deep learning, which allows computational models composed of several different processing layers to learn complex patterns and representations throughout a data set that has multiple layers to it. So with deep learning, we can see computer vision. And so, like I said, it's under this umbrella of machine learning deep learning. And the computer vision delves into how computers are able to gain a high-level understanding of images and videos. It's really cool because, like I said, machine learning is supposed to mimic humans. So computer vision is meant to mimic how we as humans are able to see and process the things in front of us, which I think is really cool that technology has the capabilities to do this. And so it works kind of the same way. It goes through iterations of training data in order to kind of pick out these things. And convolutional neural networks within machine learning is actually what allows the computer to, I guess, quote unquote, see the different images by breaking it down into different pixels, giving each one a specific label. And kind of the way that the computer decides to do that varies based on the type of computer vision model that you choose. So I mentioned neural networks. So at its basis, biological neural networks, they're up here in our brains. It communicates through electrical pulses with neural wiring, axons, synapses, dendrites, what have you, all up here in the brain. So it kind of makes sense that for machine learning, we call it an artificial neural network because we're trying to recreate what's up here. And so it's kind of works the same way. You see kind of a picture representation here. It's a network of interconnected elements that are inspired by our biological nervous system, and again, trained iteratively through known classifications. And it also just mimics kind of how our brains work as humans. So with neural networks, we see convolutional neural networks. So this is really important for object detection and pattern recognition for image tasks. So you can see kind of an example on the right of how convolutional neural networks work. So they have four main kind of layers to them, I guess we'll call them. So we have the input layer, which we can see at the beginning over here. It is the image that we input into our algorithm. It has pixel values to it. So here we can see that it's a funky drawing of the number 0. We kind of saw an example like this in class with numbers. So once it goes through that, it goes through our convolutional layer, which determines the output of the neurons, so what they're kind of seeing. And so we can have the rectified linear unit kind of looped in with that. And it applies the activation function in the algorithm to the output of the previous layer. So that kind of builds upon itself, kind of stacks up, which we can see here. Then it moves on to the pooling layers, which reduces the number of parameters by decreasing the spatial dimensionality of the input. So it kind of narrows it down to the regions of interest that you're looking for. And then that takes you to the fully connected layers, which is what actually performs that classification. So you can see here at the end, it's like, oh, it could be, 0, 1 through 9, whatever it is. And it is able to work itself through and kind of narrow it down until it gets to the output that you want. So now that we've done all this, we can look at region-based convolutional neural networks. So you can kind of see how it's all building up to what we came here for. So region-based convolutional neural networks are also known as RCNNs. So what this does is it's kind of similar to that image I kind of showed at the beginning with computer vision, is that it takes this input image and it puts bounding boxes on the image as your output. So it's kind of boxing off the outputs for what it is that you're actually looking for. So you can see an example of this with some nice cows. So these consist of 3 main modules, the RCNNs. So you look at the region proposal. So this is where a bunch of bounding boxes are put on your input image by the computer, and then it moves to the feature extractor, which it looks at each of these proposed regions and by the CNN, and it outputs a final group of what the computer decides is our region of interest that we want to look at. And then it sees the classifier, which is where the objects in each of those regions of interest that it puts out will be labeled and classified with a SVM, or a support vector machine, which is a whole other presentation worth of things on machine learning. But it is able to label these things based on the training data that you feed it. So RCNN is kind of like the basis of what I'm talking about today, but it has a few cons to it. So it's multi-stage training, so you have to look at training the neural network itself, those support vector machines, the bounding box regressors, like all those things have separate training processes, which obviously takes a really long time, which almost defeats the purpose of machine learning. We're trying to do things faster. Training for this type of work is really expensive. So each feature of each image has to be trained individually, like I said, for the SVM and the bounding box regressors, but each of those are individually extracted and written to a disk on the computer, which obviously takes up tons of storage, which is expensive. We don't like that. And it can also be somewhat slow because, like I mentioned, each feature of each object of each test image is extracted and put into the algorithm. So the overlords of machine learning decided that we needed to come up with something that was a little bit better. So naturally, we call it fast RCNN. So we have a couple improvements here over RCNN. So we have higher detection quality than RCNN, which is obviously an added bonus. The training happens all in one stage, so it's not kind of broken up by piece, which is also kind of nice. The training is able to update all layers of the network in kind of one iteration rather than kind of going step by step. And it doesn't need all those gigabytes of storage. So kind of all great improvements from what we see. So some of the main differences with fast RCNN is that instead of kind of breaking up the image and analyzing different parts of the image step by step, it goes through and takes the entire image as the input, which we can kind of see here on the bottom right. And so this obviously lends to it being faster because it's processing the entire image at once rather than in different pieces. And so they do that with several convolutional and pooling layers to create like a feature map. And from this, each object within this yields a region of interest pooling layer that extracts a vector of the feature from that map that it created. So it's going step by step in a complicated way that happens to work out. And then each feature vector is then fed into a fully connected layer at the end that branches off into these 2 output layers, which I will talk about later. But the fully connected layer is like, I guess it's the connection point. It's the beginning to the end. So I mentioned ROI pooling within this. This is somewhat of a complicated process, but it helps to increase the efficiency of the fast CRNN. So like I mentioned, it runs the neural network once across the entire image. And so once we get here with this ROI pooling, it's one of those several layers within the algorithm, and it max pools to convert any of the features that we want, the objects that we're looking at within those regions of interest into a smaller feature map, which I kind of mentioned on the last slide. And this smaller feature map has a fixed side to it, which literature has called H and W, which is can be arbitrary numbers, which most of the time I've seen it's 7 by 7. And these layer parameters are independent from that region of interest. Then those region of interest, which are looked at as the rectangles on your image, also has a label to it, that the 4 tuple. So it identifies it by the top left corner of the box and then the location of the height and the width, the small h and w. So ROI pooling basically divides these regions into sub windows by using the location of the region of interest with the feature map that it has, and then puts that into an output grid cell to move along in the algorithm. And so this ROI pooling happens independently for each feature on the map, and it's quite beneficial because it helps the fast RCNN algorithm to analyze the entire image at once, which I mentioned is one of the pros of the model. But it also allows you to be able to detect multiple objects of different classes in one output image or one input image. So if you're feeding it a picture with cars and people on a road, this kind of method will help you say, okay, I have two objects in this picture, but it will also help you say, well, one object is a car and one object is a person. So I found this image here on the bottom right, which I thought was kind of easier to digest than maybe all the things that I said. So you have your one input, goes into the CNN, it extracts the feature map. It also tells you the coordinates of your region of interest, brings it together in a pool, so the ROI pool, and then kind of stacks them all on top of each other to move to the next step, which happens to be fine tuning and the multitask loss. So this, like I mentioned, has a training process with one fine tuning stage. So it kind of cuts back on time. And so it jointly optimizes the softmax classifier and the bounding box regressors. So at the beginning, when I was talking about how fast our RCNN kind of basically works, I was saying after the fully connected layers, there were those two other output layers. That's what the soft max probability and the bounding box regressors are. So the fine tuning and the multitask loss are done by these two. So the soft max probability estimate is the classification. That's the part that is telling you this is a car, this is a person. And then you also have your real valued numbers, which I kind of talked about before, with your bounding box regression, which is, boxing off exactly what it is your object is, and then further classifying it that way. And so the whole point with this is that it jointly optimizes them together rather than individually training each component in multiple stages. So it's faster. So basically the summary of this detection with fast RCNN. It looks at the input image, has a list of the object proposals, and so then the algorithm looks at each region of interest, and it's able to output a class probability distribution with those sets of bounding box offsets relative to each region, which is kind of the end part that I was talking about. And then during training, you have this detection confidence that you assign to each region of interest for your object class, and that uses the estimated probability from those fully connected layers. And then your algorithm is able to start making predictions, which I think is really cool. So I found this one example in literature that they use, again, with the cars and the people. And so they were able to use fast RCNN to detect people. And so they were saying that this is a really big kind of topic within computer vision, especially because it can help with programming self-driving cars, video surveillance, all sorts of things. So, and I think we've used this example a few times in class too. But I thought this was really cool. So in these pictures, it's maybe kind of hard to see, but I promise there are people behind all those boxes. But the red ones are the ground truth. So that's kind of the stuff that you're feeding into the algorithm to tell it, this is a person, recognize this as a person. And then all of the green boxes are the predictions that the fast RCNN model that this group of people did actually produced. So I talked about RCNNs, I talked about fast RCNN, but that is not the end of convolutional neural networks. So past fast RCNN, we have faster RCNN, and it does essentially the same thing, but it builds off of it by integrating the entire region of interest step into the neural network itself instead of using selective search where you're kind of looking for that, what I was talking about earlier. And then past that, we have mask RCNN, which we used for the why can't I speak? The project that I was helping you with. And it's a very similar idea, but and it incorporates instance segmentation. So being able to be more specific about what exactly you're seeing instead of just kind of boxing it off in a general form. It's able to be a lot more specific, and it uses a different ROI method. but these are my references.
Okay.
And this is
Cool. I think you made a very good presentation.
thank you.
Things were very clear.
Good.
However, I have some questions.
Okay. I will try my best to answer them.
When I try to compare the architecture of RCNN and fast RCNN, can we go to that slide? Just I want to see yeah.
This
Yeah, I
one?
just want to have them together. So this is your fast RCNN.
Yeah.
And in fast RCNN, so the main thing here is with respect to the RCNN is that here you are trying to integrate both the feature map and the proposed region. And then you are trying to do ROI pooling. So for example, I have an image and I got a feature map of that image, and that image contains voids, like in our case. And then when it comes to selective search method, do you have any idea what this method is doing? And it's proposing the region? Like how, like what is the criteria to select that? So what exactly it is doing is, it is doing the same thing as you have a big image that consists of many objects.
Yeah.
And now it is dividing it into a smaller part or a smaller image. And it exactly becomes the example of where we did, dog versus cat classification in the class, where you are feeding each image. So from that, you go to that stage where you're feeding each image and it becomes to that example. But before that, we have this problem that we have a bigger image, right? So in that one, what do you think is happening with selective search method? Yeah.
Well, I would say that with like the training data, you have said, I am specifically looking for XYZ. And so I guess I would say that the selective search method is part of that, where it's, looking and through the bigger picture for the smaller things that you're looking for and selecting those smaller parts and then selecting your regions of interest from that. So it's like further narrowing it down, I guess is what I would say.
But when it makes the search, right? So is it making the search based on the edges? Is it so, for example, when the image sees it, it sees it in the form of numbers. And those numbers, say there's a car there or there's a human there. So is it doing that division of proposals on the basis of the edges, the color? What is the criteria? Because have you heard about watershed technique? Like people might have been read, in papers. It's a very, very common technique. Yeah. So like, what's the criteria? That's my.
Yeah, I think in some of the papers that I was reading, it seemed that most of the time it was looking at like the edges of things first, and then as it progresses through the algorithm, it kind of specifies it more.
Right. So you think it's coming from the edges?
Yeah.
Okay. It's coming from the edges. Also, it can group, color or texture. Yeah, it can choose a criteria, and based on that, it just says that it's a different thing.
Yeah, I think I saw another paper too that used it for medical uses. They were looking at like, I don't remember what they called it, but it was something like inside your intestines that was not good. And they were using the algorithm because they were saying that it's helpful to be able to determine whether or not someone like has this, I guess, disease, because it was hard because the actual, I guess, disease itself popped up in different sizes and shapes and textures, like you said. And so they were doing the thing where they were, for their training data, they were shrinking and making the big image bigger and rotating it to help train it to be able to identify the disease, I guess. So I would say it's along those lines.
Right. So it's just doing on different criteria. Maybe if the two things have a same color, it's, it tries to pick those pixels and take them as maybe this is, same things. Maybe if two things have a similar textures, it would be your, your edges and everything, it would try to make them as a region
Mhm.
and try to give them the same, maybe same weightage or same
Mhm.
same segmentation. You cannot say at this stage because it's early, but it's
Yeah.
just making it as the same object.
Yeah, I guess that makes sense too. Because I guess in my head, when I was thinking of the region of interest pooling, it was like, oh, it's solely based on like what it will, well, I guess what it looks like, that makes sense. But like, I guess what I'm trying to say is it makes sense that your region of interest could be by shape, it could be by color, it could be, it doesn't have to be like black and white. Like you could have several different things, which I guess is the beauty of it. Because you can tap
So
into a lot of stuff.
now you have got those proposed regions where you had an image consisting of, say, cars and humans, and now humans and cars, you are giving it a proposed region. At the
Mhm.
same time, you are giving it the entire image, you are giving the feature map. That means you have converted the entire image into numbers already, right? And now they are doing ROI pooling. That means the region of interest and feature map, so wherever your feature map that contains the region of interest, that would be in terms of numbers. So you know what I'm trying to say? You have to imagine a chart which has numbers, and other chart, it contains the proposed regions. And now the chart with the numbers, the pooling starts happening there. So in term of pooling, what happens is, again, we are reducing the size so that we can apply all these fancy probability estimates. So now you got a kind of pooling from each region of interest. Now on the screen, I see there are three FC written. So fully connected layer, there is one, and then there are again two fully connected layer. So if you remember, the fully connected layer, basically they have neurons in them. That means all the number sheet that you have generated, where you have given more weightage to the areas which contains the object, is now converted into a linear matrix. Remember where the image used to convert into a linear matrix, and now this is getting fed into the neurons, right? So then there are two things happening, but what puzzling to me is, maybe we should cross check that why it's written 3 times fully connected layer, or is it doing the parallel operation? That's why it is just shown for the display purposes.
That's kind of how I interpreted it. But I'm not 100% sure why that, I didn't make that. I took it from the paper.
Right. So this fully connected layer, they are responsible for that regression, and those fully connected layer are responsible for those classification. And they are simply, we are putting those numbers, and it's getting into the neurons, and neurons are computing it, that this is a high probability here, that, that this is certain object, or this is high probability here, we put the bounding box. I think it's clear. Just my question was that why we have 3 FC layer. Yeah.
Yeah, I think, yeah, again, I took that from somebody else. I didn't make it. So the way that I read it is that those things are happening kind of simultaneously, but for, like you said, visualization purposes, they kind of split it up that way, just so you can kind of see everything.
Right.
But
so this is your faster RCNN. Now we go to fast RCNN, the RCNN diagram. The RCNN.
this one?
Yeah. So RCNN, yeah, so this is normal CNN. So now here we are going to RCNN. And in RCNN, your region proposals, so again, they are based on what algorithm? Like you have an idea, like how, when you give it to your computer, what is the algorithm it's choosing?
Yeah, well, okay, so when I was reading through stuff, a lot of it seemed that like when you put your image into the algorithm, it would put tons of these boxes onto it and then narrow it down from there. Like I saw a few pictures that had like just so many different boxes, so many different sizes and shapes. And so I guess the way that I interpreted it to work is it's looking at all these different boxes, and then based on like the training data that you're feeding it, it's narrowing down like which of those hundreds of boxes actually has something in it worthwhile to look at.
Yeah. So the main difference, okay, if we even say that we are proposing region by some algorithm, then the main difference between two algorithms is that we have got 3 convenites, or we have got multiple convenites depending upon how many regions are proposed, right? It's not single convolution layer. You have for each proposal you have a separate layer, right? So that's what makes it complicated. But then at the end you see something as SVM, support vector machine model. Any idea how is that working?
Well, I'll be honest, I didn't really look too much into SVM.
Just classification. It's just classification. Yeah. So in your thing, you were using those softmax and everything that were classically told to you. So in SVM, it's a similar kind of classification where you know, you literally can separate things, or you can separate two kinds of classes by putting a line, and that line has got a distance from them. So it's just, you know, on a chart, for example, you have apples, oranges, bananas, and now somebody tells you to just draw a line to separate them. So it's using that algorithm. So it was used. And any idea why this algorithm is no more used?
Well, I mean, I would say that just because it seems rather complicated when you have other models that will kind of do everything all at once. And it sounds to me that just regular RCNN is faster than what could be done by you or me, but also a lot slower in comparison to other later models.
Right. I think your presentation was one of the most clear presentation I saw. It was
good.
Yeah.
Good. I'm glad to hear that. I'm glad it made sense.
Yeah, I mean, there were not too many questions, honestly, because it was well explained for large part.
Good. Well, thank you.
I have questions also.
Yeah, go ahead.
Yeah. For the RCNN, I guess Jonathan also mentioned some selective search algorithm. And do you have an idea about which framework and dataset are used for the RCNN and faster RCNN, differences of them?
The difference between RCNN and fast RCNN?
Yeah, I mean, which framework and datasets are used for the both RCNN and faster RCNN?
Oh, okay. I mean, so from my understanding is that you could use the same input data for both. It's just how you get to that final result that's a little bit different based on the two. So yeah, I mean, I guess that's my answer. I kind of already explained how that works.
Yeah. Actually, I expected, like, for example, darknet or the other, you know, ImageNet, etc.
Yeah. So okay. So that was like when the models were initially trained in the papers. So there are like, you know, there are like famous data sets like ImageNet, Pascal VOC. So there are like 14 million images trained of the world.
Okay,
So,
I think I saw, I was reading the paper by the guy who developed fast RCNN, and I'm pretty sure it was did you say Pascal?
Pascal, yeah, Pascal VOC.
Yeah, I think it was that one.
Yeah.
Okay, for both RCNN and faster RCNN?
I don't know about RCNN, but for fast RCNN, yes.
Okay. And the other thing is, I presented also YOLO, and I mentioned also RCNN a little bit. Also, I compared between the YOLO and RCNN, and it seems that YOLO is better in my presentation. What are the superior properties of RCNN? What do you think about this? Do you have any comment about it?
Oh, sorry, could you repeat the question about what?
I presented YOLO, and I compared both YOLO and RCNN, and it seems that YOLO is better. In my presentation, I said that YOLO is better, because of the features of it. What are superior properties of RCNN? Do you have any comment about it? And for example, why we use also faster RCNN, because faster RCNN is better than the RCNN, right?
Yeah, so that's kind of what I was talking about here on this slide. So
Mhm.
it has.
And do you have an idea another, for example, YOLO, why RCNN is better than YOLO, for example, for you? Because I think that YOLO is better than RCNN, for example.
I don't know because I did not look into YOLO, so I'm sorry.
Okay, okay. So superior properties of RCNN then, faster RCNN, when you compare the RCNN and faster RCNN.
Right here.
Okay.
Yeah, I think
I don't know if you wanted me to
YOLO,
like explain it again, but
yeah, YOLO
Okay.
is
Okay.
YOLO is superior. YOLO is state of art.
yeah,
It's much more
It's-
faster. It's much more faster. It
yeah.
has got
Mhm.
more deeper coordinates. Yeah. So, but
And
everything came as a series of development, but until and unless you apply it on your data set, so all these algorithms that you are learning, and I'm emphasizing, they
Mhm.
all are systematically applied on our microscopy images. Like all of them, like 8 or 9, we talk about all versions of YOLO, all version of faster RCNN. There are papers that uses all these algorithms. Some of them, they work better with one of them, and other they're not. For example, the YOLO version V7, which is the latest one.
Mhm.
So in your images, you have the voids, and voids are overlapping on each other, right?
Yeah.
So how do you detect those kind of objects when one object is occluded by the other, right?
Mhm.
So that kind of things, these kind of algorithm, they won't work. But the algorithm which have taken into account the loss functions, where your occluded objects can be defined. That means the object that is on the behind, it's hidden behind. For example, if I'm, having a book in my hand, so I want my book and my face both to be detected. So in those kind of algorithm, and these kind of things are very valid in microscopy images, because one is hidden over the other. So in some regions they also have dislocations and some little part of the void. So for those kind of data sets, YOLO V7 is used. So depending upon the data set you have, even in the microscopy images, if you give a very clean data, any algorithm would work. But if you give a little bit tough data set, where you have grain boundaries, dislocation, voids, and round bubbles, you have to test that which algorithm would work, right? So that was the purpose of this activity.
I will say too that fast RCNN isn't even the superior RCNN. Like there have been, like I mentioned at the end, there have been like other better models that have been built off of that.
Yeah.
And
So yeah, as the complications in the data are increasing, right, we have to put in more. These are like little, subunits that we have to attach to the previous one. Yeah. Well, very nice. I think it was very well done.
Thank you.